They are the most common type of planet in our galaxy, making up about 30% of all exoplanets we've discovered. They're larger than Earth but smaller than Neptune. But here's the problem. We have no idea what they really are. Are they rocky worlds with incredibly thick atmospheres? Are they water worlds covered in oceans thousands of kilometers deep? Or are they something else entirely, something we can't even imagine? The biggest issue is that we have nothing to compare them to in our own solar system. There are no mini-Neptunes orbiting our sun, so we're studying planets that, by our local standards, shouldn't exist. And yet, they're everywhere, and we don't understand them at all. Mini-Neptunes are defined as exoplanets with a radius between 2 and 4 times that of Earth, but that's where the similarities end. Their masses vary wildly. Some are only a few times heavier than Earth, while others are 10 or even 15 times more massive. This creates an incredible range of densities. Some mini-Neptunes are almost as dense as our own planet, while others are as light and fluffy as styrofoam. Take the planet JWST 193b, discovered in 2024. This world is 50% larger than Jupiter, our solar system's giant, but it weighs only 14% as much. Its density is a mere 0.059 grams per cubic centimeter. To put that in perspective, cotton candy has a density of about 0.05. This planet is essentially a giant cloud, a cosmic puffball. How does a planet even become that light? We just don't know. The leading theory for many of these strange worlds is that they are water worlds, not planets with oceans like ours, but worlds where water makes up as much as 50% of their entire volume. And we're not talking about the kind of water you'd go swimming in. We're talking about water in its most extreme states, supercritical water, vast steam atmospheres, and high pressure ices hotter than an oven. The best examples we have so far are Kepler 138c and Kepler 138d. These are two planets orbiting a red dwarf star 218 light-years away. They are both roughly 3 times the size of Earth, but only have twice its mass. That makes them far less dense than a rocky world should be. In 2022, after careful study, astronomers concluded they are very likely water worlds, but they're not covered in surface oceans. Instead, they are thought to have incredibly thick steam atmospheres, thousands of kilometers deep. Beneath that scorching steam, there might be a layer of liquid water, or perhaps supercritical water, a bizarre state where the line between liquid and gas completely disappears. And deeper still, you'd find high pressure ices. This is water that remains solid at hundreds of degrees Celsius, simply because the pressure is so immense. These are not Earth-like planets. They are profoundly alien. Then there's the famous K-18b. This is a mini-Neptune, about 8.5 times the mass of Earth, orbiting right in the habitable zone of its star. In 2023, the James Webb Space Telescope detected methane and carbon dioxide in its atmosphere, which got a lot of people excited. Some scientists even suggested it could be a Hycean world, a planet with a hydrogen-rich atmosphere covering a vast, globe-spanning liquid water ocean. A world where life, as we know it, could potentially exist, but science is a process. In 2024, follow-up studies started to challenge that exciting idea. New models showed that a lifeless Hycean world just couldn't sustain the high levels of methane that were detected. So, if K-18b really has that much methane, it means one of two things. Either it has a biosphere actively producing methane, meaning it's alive, or it's not a Hycean world at all. It might just be a gas-rich mini-Neptune with no surface and no ocean, just gas all the way down. We still don't know which it is. Here's what makes mini-Neptunes so fundamentally strange. In our solar system, there's a very clear divide. You have small, rocky planets like Earth and Mars, and then you have the massive gas giants like Jupiter and Saturn. There's nothing in between, but mini-Neptunes occupy that exact middle ground. They seem too big to be purely rocky, but too small to be full-blown gas giants. So why does this middle ground exist everywhere else, but not here? One clue comes from something called the radius valley. When astronomers plot the sizes of all the exoplanets they've found, they see a strange gap. There are very few planets with a radius between 1.8 and 2 times that of Earth. Planets smaller than that tend to be rocky super-Earths. Planets larger than that are usually mini-Neptunes with thick atmospheres. This gap suggests some kind of process is at work, something that's actively shaping these planets. The leading theory is atmospheric escape. Planets orbiting very close to their stars are blasted with intense radiation. This radiation heats their upper atmospheres, giving gas molecules enough energy to escape into space. Over millions of years, the entire atmosphere can be stripped away, leaving behind a bare, rocky core of super-Earth. But if a planet is massive enough, its gravity is strong enough to hold onto its atmosphere. Even under this intense stellar bombardment, it remains a puffy, gas-rich mini-Neptune. This process could be what creates the radius valley, this dividing line between rocky worlds and gassy worlds. But it also raises a disturbing question. How many of the mini-Neptunes we see today are to be much larger gas giants that have lost most of their mass? And how many are still shrinking, destined to become barren rocks? The atmospheres of these planets are just as bizarrely diverse as their sizes. Observations from the James Webb Telescope have revealed a wild array of compositions. Some mini-Neptunes have crystal clear atmospheres, while others are shrouded in thick, impenetrable hazes. Some have high concentrations of carbon dioxide. Others are rich in methane, water vapor, or even sulfur dioxide. Why so much diversity? One possibility is that it all comes down to where they were born. Some mini-Neptunes might form far out in their star systems, beyond the ice line where water freezes solid. They gather thick mantles of ice and then migrate inward, closer to their star. As they get closer, the heat vaporizes the ice, creating a thick, steamy atmosphere. Other mini-Neptunes might form closer in from the start, with less water and more rock, but still manage to hold onto enough gas to puff up. We don't know which scenario is more common. It's likely that both are happening all over the galaxy. So, what would it be like to actually visit one of these worlds? Let's imagine a journey down into the atmosphere of a water world like Kepler-138d. From a distance, in space, the planet is a pale blue orb, shrouded in thick, swirling white clouds. As you begin your descent, the sky around you brightens, but it's not blue like Earth's. It's a brilliant, uniform white, heavy with water vapor. The temperature climbs steadily. 100 degrees Celsius, 200, 500. You are falling through a steam atmosphere that's thousands of kilometers deep. The pressure builds relentlessly. 10 times Earth's atmospheric pressure. 100 times. 1,000. At some point, the steam transitions into liquid water, but you wouldn't even notice. There's no splash, no surface. The change is gradual, as the steam becomes a supercritical fluid, a state that is neither liquid nor gas. You keep descending. The pressure is now 10,000 times what you'd feel on Earth's surface. The temperature is over 1,000 degrees. And yet, The water is still all around you, a strange, dense fluid. Eventually, you reach the deep interior. Here, the pressure is so extreme that water is forced into exotic forms of high-pressure ice. Ice 7, Ice 10. This is solid water, but it's hot enough to melt lead. And somewhere, deep beneath it all, lies a rocky core. If you tried to land on this planet, you would never find solid ground. You would just keep sinking through steam, through supercritical fluid, through exotic hot ice, until the crushing pressure obliterated you into nothing. Mini-Neptunes are a cosmic warning. They show us that planets are far more diverse and strange than we ever imagined. Earth is not the template for planet formation. It might be the exception. Most worlds in the galaxy are nothing like our own. They are too big, too light, too hot, too weird. And we are only just beginning to understand them. The James Webb Space Telescope is giving us our first real look into their atmospheres. But every new observation seems to raise more questions than it answers. Why are some hazy and others clear? Why do some have so much carbon dioxide? Are any of them truly water worlds with deep oceans, or are they all just different flavors of gas planets? We don't have the answers, and that is what makes them so fascinating and a little terrifying. The most common type of planet in the galaxy is a complete mystery. Thank you for exploring the enigma of mini-Neptunes with us. Subscribe for more journeys into the unknown. Until next time, keep looking up.